Welcome to the Virtual Wide Area Network mobile use case. If, prior to viewing this video, you have not watched our introduction to Virtual Wide Area Networking, then please stop now and review it first. It will help you to understand the features discussed in this video with greater context. In this use case, Apollo server software is deployed at the edge of an enterprise LAN or on one of many edges present in a carrier network. Apollo client software is loaded onto a PC, a smartphone, or one of many variants of mobile appliances. When the client and server are connected via a virtual wide area network, the mobile device receives an IP address from the client node that is assigned to it by the server node. From that moment onwards, the mobile device behaves in every respect as if it were on a subnet of the remote enterprise or carrier network. Bandwidth, resilience and latency between the mobile device and the remote network can be enhanced by bonding two or more wide area networks together, such as 3G networks, 4G networks, Wi-Fi and satellite connections. For example, this feature is important to users who need to stream surveillance video or to service providers who want to increase the quality of experience for their unified communications applications. Connectivity is maintained seamlessly as the mobile device changes bearer, such as when moving between 3G and Wi-Fi or between 3G and 4G networks. This feature addresses problems currently being experienced by carriers seeking to offload traffic from congested networks and by enterprises seeking to control the cost of their employees' mobility by using least cost networks. We'll start with a demonstration of the Apollo software running on a PC. Apollo's client software installs as a network interface on a PC. It is configured to connect to an Apollo server located on the edge of an enterprise network. In this example, I have set a policy for the client to bond multiple networks together and present the aggregated bandwidth to the applications. When Apollo is configured this way, the bandwidth of all available networks is aggregated and traffic is shaped to use the networks in the most efficient manner, with due consideration to the real-time performance of each network and the traffic type being presented. As networks become available, their performance is tested and their bandwidth added to the available pool. As networks are lost, their bandwidth is removed from the pool. In this example, a tool built into Apollo's client shows the traffic shaping as it occurs across three wide area networks, a Wi-Fi network and two EVDO networks, one Sprint and one Verizon, whose bandwidth is being bonded together. At this point in the trace, the Wi-Fi connection fails. Because of its superior performance back to the server, the Wi-Fi connection has been carrying all of the traffic. Now Apollo moves the traffic to a combination of the two EVDO networks. A little later, we see the Wi-Fi interface become available once again. Apollo tests its performance and moves the traffic from the two EVDO networks back onto the Wi-Fi connection. Between these two events, the traffic is being shaped across the two EVDO networks. Note how Apollo moves traffic between the two networks as their performance changes. The blue trace represents the uplink data and the green the downlink. In this second example, there are two EVDO connections available for the virtual wide area network. They are both bonded together. Apollo is continually measuring and assessing the performance of each of these networks. In this section of the trace, the performance of the Sprint EVDO network is dropping off, possibly from increased co-channel use or decreased signal strength or increased packet loss. When the performance reaches a point where Apollo assesses that the network has reached its minimum threshold, the Verizon network represents the most efficient path and traffic is moved to use it. In this example, a network preference policy is set for the client to roam between networks. Connectivity is preferred by the LAN interface first, followed by Wi-Fi, then Sprint's EVDO network, and finally Verizon's EVDO network. The client establishes a connection to the server over the highest priority network available and queues lower priority networks as hot standbys. When the preferred network fails, Apollo seamlessly moves the communications over to the next highest priority network available, which in this example is Wi-Fi. When the Wi-Fi network fails, Apollo moves the connection over to the Sprint EVDO network. And when that fails, the connection is moved over to Verizon. When a higher priority network becomes available, the connection is moved seamlessly to use it. Apollo's PC client software also includes a SIP voice over IP and video client that is provisioned and configured via the Enterprise AAA server. There is zero configuration on the client machine, and the user's PBX profile is driven by their login credentials. This means that if multiple users use the same PC, each will receive a custom profile for their voice and video communications. All features of the Voice over IP application, as with all aspects of the Apollo client, is configured and provisioned through an intuitive radius database. In this example, the phone's codec is being configured. The second mobile use case will focus on an example of Apollo's smartphone functionality. This picture shows Apollo installed on a Windows mobile smartphone, the HTC Touch Pro. The Touch Pro has a Voice over IP client enabled and configured to connect to an enterprise PBX, which is behind the enterprise firewall using a private IP address space. Because there is no virtual wide area network enabled at this time, the Voice over IP client shows that there is no service. This device supports a 3G EVDO interface and a Wi-Fi interface, but will not allow bonding of both together. Apollo is configured to prefer a Wi-Fi connection to the server when it is available, or else to use the Sprint EVDO network. In this use case, Apollo is not configured to connect automatically. This function is left to the user. When activated, Apollo checks to see what networks are available. At this point, there is no Wi-Fi available, and so the connection to the server is established over the Sprint EVDO network. When Wi-Fi becomes available, Apollo seamlessly switches the data session to it, placing the EVDO network on hot standby. As you can see, the Voice over IP client is now on the enterprise network and can see the PBX on its private IP address. One of the most important features of Apollo's smartphone client is its ability to manage power consumption on the device. In this example, the smartphone has been allowed to enter its power save mode. When an incoming SIP message is received by the Apollo server, it is forwarded to the client, which raises the smartphone from its power save mode. This functionality is an essential requirement for the mobile Voice over IP quality of experience, since without it, the mobile device is restricted to only making outgoing calls or must risk continuous power drain from maintaining a high power consumption state. Throughout its operation on a smartphone, Apollo gathers statistics about the data usage of the device, which it shares with the server for collation and analysis.